Hmm. Okay. Hello, I'm Benyu Wang from Tsinghua University. Today I'm going to talk about our work about vertex connectivity problems on STOC 2023. And this is a joint work with Zhiyi Huang, Yaowei and Thatchaphol Saranurak. We begin this with an overview of our paper, and also we introduce what is vertex connectivity and what's our results. So first, connectivity. We all know that edge connectivity and vertex connectivity are both really fundamental concepts in graph theory. So here we can define the edge connectivity or vertex connectivity in the flow view by the edge disjoint or vertex disjoint passes, or also in the cut view by a minimum edge or vertex cut. So here in this paper, we consider undirected unweighted graphs. Also, given the source and sink U and V, we know that both edge connectivity and vertex connectivity can be computed in one mass flow. So ST vertex connectivity is in near time. And we'll see that there are 5 variants of connectivity problems in the literature. The first one is global connectivity, and also ST we have mentioned, and also standard connectivity, single source connectivity, and also all pairs connectivity. In our paper, we consider the results for all these schemes and gives a total answer. So we can look at this table, which are generally the complexity of edge connectivity problems versus the complexity of vertex connectivity problems. For edge connectivity, we can see that regardless of global, single source, all pairs, or standard, when we refer to all pairs edge connectivity, we actually says that it's the Gamma-Hu tree problem. So we can see that the edge connectivity problems are easy and they are in the near-linear scheme with some recent results. However, for vertex connectivity problems, we know that global vertex connectivity can be computed in near-linear time. However, for these new variants, the single source, all pairs, and standard, we really don't know that much about these problems. So there's a question that since edge connectivity problems are all in the almost linear scheme, what about vertex connectivity problems? Are they still easy or much harder than the edge connectivity problems? Uh, we can give this open problem that can we solve all variants of vertex connectivity problems in almost linear term too? However, in our paper, we show that this hope is false by giving some lower bounds for these vertex connectivity problems. So we can see in our paper that, in fact, vertex connectivity problems are generally much more harder than edge connectivity problems. So this is our result. Okay, so I will mention our results on vertex connectivity problems below. In our abstract, we can see that for these vertex connectivity problems, for all pairs and standard connectivity, it is omega hat N4, which is the exact complexity. And also there's a hat on the omega. The hat means that we ignore the small O1 factors. And also single source, it is with exact bound theta hat n cube. And also for ST and global connectivity, the exact bound is theta hat n square. And also for graphs with general density, we use parameter m, and the tight bounds are theta hat m square, m to the 1.5, and also m, compared to the n4, n cube, and n square. So this these bounds for general density, we assume that the Gomerhu trees for element connectivity can also be computed in almost linear time. So we want to fill in the tables, and first for the at least dense graphs, we can fill in the graphs here. So first, for single source, the time complexity is n cube, and also for all pairs and standard, the time complexity will be zeta hat n4. So for the upper bounds, there seems trivial that we just call n or n square max flows to solve them. But for the lower bounds, they are the main part of our paper, and we will prove them below. Also for general density, we obtain these results. So for edge connectivity, they are in all almost linear, but for vertex connectivity, uh, first the new upper bounds are just for single source, it is O hat m to the favor 3, and for all pairs and standard, it is O hat m to the 2.2. If we further assume the Gomerhu tree for element connectivity can be computed in almost linear time, then we obtain both tight lower bounds and upper bounds for these problems for the graphs with general density. We can see that for single source, it is zeta hat m to the 1.5, and for all pairs and standard, it is zeta hat m square. So these are our results in this paper. Okay, so let's go on to the main part of our paper and our proof, which is the lower bound for APVC. Here, APVC is short for the all pairs vertex connectivity problem. First, some notations, and I will just read the slides quickly. So below, we use the following notations in a graph G. We use VG and EG to represent the vertex and edge set. Also, we use kappa G UV to represent the UV vertex connectivity. And also for vertex V, we let NGV denote its neighbors in graph G. And also let NG bar V denote its non-neighbors. Moreover, we use VC to be short for vertex connectivity. And so APVC is short for all pairs vertex connectivity. In the all pairs vertex connectivity problem, we are just asking the connectivity U and V for every pair. So these are some notations, and okay. The next one is the Four-Clique conjecture, and our proof is based on the Four-Clique conjecture, which is a popular conjecture in, I think, fine-grained complexity. So it generally says that for the problem, for the Four-Clique problem, which refers to a problem finding a Four-Clique in a graph G, we have an omega n to the 4 minus epsilon time lower bound, or no combinatorial algorithm can solve it in O n to the 4 minus epsilon time for any epsilon larger than 0. Here we remark that the combinatorial algorithms, the combinatorial means that the algorithm do not involve fast matrix multiplication. So if we use we use the fast matrix multiplication, then the time bound will be I think O n to the omega 1 to 1, where it is some result in rectangular matrix multiplication. So the conjecture also have a version for general algorithms, which is omega n to the omega 1 to 1 minus epsilon. This is for general algorithms, so it is still considered supercubic. Now we go on to our main theorem of APVC. That is, we first assume the Four-Clique conjecture, that we cannot solve Four-Clique very fast. Assuming this, we give a result that the all pairs vertex connectivity problems also has an omega n to the 4 minus epsilon lower bound for combinatorial algorithms. So the proof is generally from a reduction from Fock-Leak to APVC. So we know that if APVC is easy to solve, then also Fock-Leak is easy to solve. So we begin our reduction idea. First, given a Fock-Leak consistent G, we can also construct a four-parted graph G4P. The graph G4P is constructed by first duplicating the vertex set VG into four parts A, B, C, and D. Also, we link edges between these four parts A, B, C, D according to the edge set EG. Therefore, one can see that G has a Fock-Leak if and only if G4P has a Fock-Leak, since their Fock-Leak are just corresponding to each other. We can remark that the four-parted graph G4P is hard if G is hard. So actually, when we think about the Fock-Leak conjecture, we can also think that okay, the Fock-Leak instance is a four-parted graph, is any four-parted graph, and the hardness is still valid. So first, we consider the graph G4P with four sets A, B, C, and D. And now, we consider two nodes A in A and D in D. Maybe there's an edge between A and D. And also, we denote BA and BD, B subsets in B being neighbors of A or D. That is, maybe NGA or NGA cap B or NGD cap B. So also CA and CD are subsets in C being neighbors of A or D. Uh, Using this, we can show that there's a Fock-Leak in G4P or in G. If and only if for some edge AD, there's also an edge from BA cap BD to CA cap CD. We can prove this by just by the definition. So by the definition of BA, BD, CA, and CD, we know that the pairs AB, BD, AC, and CD, there are four edges. And we suppose AD is an edge, and there's an edge from B to C. So therefore, there is a Fock-Leak with six edges, uh, and we can prove this conclusion. So below we can have a oversimplified example just from this one that we link A to everything in BA cap BD, BA intersecting BD, and D to everything in CA cap CD. We can see that if there's an edge in between the middle two parts, then A and D will be connected. Otherwise, A and D will be disconnected. So therefore, we can say that if the sets B cap BD and C cap CD has an edge, then the vertex connectivity of A and D is at least 1. And if there's no, then the connectivity of A and D is 0. So we can capture the existence of a Fock-Leak between the containing the edge AD by the connectivity in this graph. So this is the reduction idea we can from vertex connectivity computing, and we can get the information about whether there's a Fock-Leak or not. But yeah, obviously this is what we dream about, what is oversimplified. We actually we cannot we obviously cannot uh replicate BA cap BD and CA cap CD isolatedly for every pair A and D, since then the number of vertices will be, I think, n cube. So that's too large. We don't want that. And we want also two common sets B and C, but these BA cap BD and CA cap CD sets are generally from the set B and C, and they are just filtered out. So we use two set intersection filters to do this. That we filter out BA cap BD and CA cap CD from two common sets B and C, and make sure we can capture the connectivity in the new graph by the complexity of the whole graph. So this is the two set intersection filters. They just simulate the sets BA cap BD and also CA cap CD. So let's begin the introduction of our set intersection filters. Yeah, first, we can just simulate BA cap BD the set. For CA cap CD, it is really similar, and we will ignore the part and just look at the upper part's proof. Okay, so on the left, it is what we call a set intersection filter, and we do not need to go into details of its construction for now. I just want to say that on the right part, if we suppose the lower square is maybe something like say cap CD, and this one will be our oversimplified example that we dream about. So let this let the set intersection be PBAD, which is green, and also we have a rest part of the graph R, which is in blue, and we will show that uh, we can capture the connectivity in RBAD, which is purple on the right, and like the graph which we dream about. So we can capture the connectivity in RBAD by the connectivity in the whole graph PBAD cap R. No, PBAD union R cap R. So actually, the dilemma just saying that the connectivity in R cup PBAD, which is the whole graph, is the connectivity of RBAD, which is a simplified graph we dream about, adding something. Some variance only depend on A and D and can be computed efficiently. Yeah, so let R be any graph with a set B, and PBAD. In PBAD, we have a duplicated set B prime, and it is shown in the green part. So let's begin with the construction of the set intersection filter. PBAD, we can see that there's only one node A and only one node D. And also there are two sets B, which refers to the set B in the original instance G for P, and also B prime, which is a duplication of B. So let us link the red edges first. We link A to everything in B, and link a matching in B to B prime between duplications. And also we link edges from D to set B prime. So they are common and do not depend on the edges in the graph G4P. Then we link something according to the graph G4P, but not strictly according to that. We can see that for the set BA, which is the neighbors in B of A, we link an edge from A to the set B prime. Yeah, note that it is B prime and not B. So also for everything in B that is non-neighbor of D, which is the set BD bar, we link D to the set BD bar, and as the red edges goes. So this will complete our construction of the set intersection filter. And we will prove our lemma of this filter below. Okay, so let's go on our filter, and first what we call something in the paper above is generally this one. It is the size of BD cup BA bar and also, or maybe BD cap BA bar. I'm sorry, here's a mistake. And also the pink one, which is BD bar, and also the yellow one, which is BA. So actually, there's an addition of RBAD with these ones, and they will form the complete connectivity in the whole graph R cup PBAD. We will see. We will see this in both flows and cuts. So if we can construct a flow and also a cut, we can prove this equality. So first I will show that okay, this is cap, and also we will construct the flows first. So for these red flows, we can generally go from A through the node in BD cap BA bar and uh, go through the matching edge and go to B prime and then go to D directly. So as shown in the red passes. For the purple one, the BD bar, we simply goes from A to the set B to a node denoting one in the BD bar, and then to D. Also for the yellow ones in BA, we go from A through B prime to the set BA and then go to D. So we can see that with some extra passes for, in RBAD, actually they sums to they can sum to vertex disjoint path set in the whole graph R cup PBAD. So this is from the flow construction view. And also from the cut construction view, for the red ones and pink ones and yellow ones, we can cut these nodes according to the graph, such that for BD cap BA bar, we cut the set in B, the red node. And for BD bar and BA, we just cut the every node which is linked to both A and D, the pink ones and the yellow ones. Okay, so we can see that the remaining white ones are just in B, which is in this set BA cap BD. And also in B prime, that is in BA bar. But we know that the nodes in BA bar in the part B prime is not important because they are only connected to D in the rest graph, and we can ignore them. So therefore, when we consider what the graph look like in the remaining parts after the cut, we will see that A is linked to the middle part of B. That represents the set BA cap BD, which is generally the one in RBAD. Yeah, so if we compare the parts in the remaining parts in R with the red and pink nodes cut, we will see that it is just the set RBAD. So actually, with a cut in RBAD, we can give a total cut in the whole graph R cup PBAD. Then we know that uh, from uh, from a cut view, the this inequality is also true. So we can say that okay, we can capture the connectivity in RBAD, which is a model we dream about, by actually the connectivity in PBAD and R, where B is a common set for all A and D, uh, and we can simulate or filter the set BA cap BD out, so it becomes RBAD. This is the idea in our setting satisfaction filter. Uh, So therefore, with some additional errors, we can suppose the graph is RBAD by just computing the connectivity in R cup PBAD, the whole graph. So this will finalize our proof of the set intersection filter lemma. We can see that we can capture the connectivity in RBAD, the red one, by the connectivity in the whole parts R cup PBAD, which is the left one, the green one, adding the blue one. So also we can also construct another set intersection filter PCAD for the set CA cap CD and let them link to D. So as the graph RBAD shows, we can suppose that the part below, the small rectangular below, is CA cap CD and linked to D, and then the graph RBAD will become our oversimplified example, and we only want to check if there is an extra flow or an extra edge between BA cap BD and CA cap CD. So this is the set intersection filter. And so it just simulates BA cap BD and CA cap CD, and we can go to our oversimplified example. Then I will introduce another thing called the sourcing isolating gadget, because if with set intersection filter only, it is valid in only one source A and only one sink D. However, we now consider multiple sources in a set A and also multiple sinks in a set D. In fact, there may be some passes we don't want to have in the graph. So the sources or sinks may interfere with each other. We can look at this example why an addition of another source A prime will let the set intersection filter lemma be not true. So we can see that okay, in our proof we cut everything in BD in B. No, BD cap BA bar in B, and also the pink ones and yellow ones in B and B prime. However, there may be some a prime that first it is linked to the white one in BA cap BD, but also it's linked to some other one in the set BA bar in the part B prime. So maybe so there may be also an extra pass we do not want to have, that is from A to the set B and then to the node A prime, and then goes to the part B prime and finally to D. So this is not totally RBAD. So we can see that with some more sources or sinks, we can have some cases which is much more complex. So the idea is that we isolate the pair A and D from everything else in A cup D. So we can view the graph. Actually, we can, when we consider the connectivity of A and D, we can safely cut or say ignoring the existence of A prime and only treat it as only one source and only one sink here. So how to do this? We have a tool called the sourcing isolating gadget. In fact, this tool is from a paper that is telling the oracle complexity of vertex. No, the space complexity of the vertex connectivity oracles. So this is quite interesting. We get some tools in space complexity, and we use them actually modify them for time complexity. So we begin our introduction of the sourcing isolating gadget. We can view the graph on the left, that is R. We first have any graph R with two sets, the sourcing big A and the sink set big D. There's a sourcing pair A and D which we wish to compute the vertex connectivity between them. Now, we add a sourcing isolating gadget Q, which is the red part. Uh, and the other parts in Q, except A and D, it's not linked to everything else in R. So uh, actually, we can also dream about a groove RAD. The graph is very simple that for the source set, there's only a source small a, and for the sink set, there's only a sink small d, and everything else are just cut or ignored. So dilemma says that okay, we can capture the connectivity in RAD, which is the graph we dream about, and we can apply the set intersection filter on it by the connectivity of the whole graph R cup Q with the source sink isolating gadget. And the connectivity in the whole graph R cup Q is in fact the connectivity of the graph RAD with only one source and one sink, adding the sets of A and the sets of D. So this is why we call it source sink isolating gadget. That is from the gadget adding the gadget Q, we can suppose that we isolate the nodes A and D from the source set and sink set big A and big D. And the graph will become RAD with only single source and single sink. Okay, after the illustration, we begin the construction of the source sink isolating gadget. The gadget is like the left one, the construction. And yeah, we can see that the A1, A2, and D1 and D2 are generally out of or do not link to the green part, the rest part in R. We can illustrate it as the graph on the left. So first, the sets A1 and A2 are duplications of the source sink A. And also the sets D1 and D2 are duplications of the sink set D. And this is the construction of Q only based on the two sets A and D. So for the edges, we link some bipartite cliques. You can see from A2 to A and from D2 to D, and also from D1 to A and A1 to D. So there are four bipartite cliques. And also we link some matching edges from A to A1 by the original A and the duplication A1. And also between D1 and D, between the original D and the duplication D1. So this is generally the construction of the source sink isolating gadgets, and we can view the blue parts are consistent in the left graph and the red graph for illustration. So below we begin our proof of the lemma on the bottom of the page. That is kappa R cup Q AD is kappa RAD AD adding the size of A and the size of D. We also prove this lemma in a flow cut manner. That is, we first construct vertex disjoint passes and then construct cuts that meets these requirements. So the first one, we consider constructing a flow in R cup Q, the whole graph. First, we have this green pass, only one green pass, So from A, we can go to the duplication A1 in the set big A1, and then to the sink D. And also for everything in the set A other than the source A, we can actually have a prime and let A1 prime and A2 prime be duplications of A primes in the sets A1 and A2. Actually, we can have an extra path that from A goes to A2 prime and then to A prime, then to the duplication A1 prime in the set big A1, and finally to D. So there are sets of A minus 1, A primes, and so we all know that these will form sets of A minus 1 internally vertex disjoint passes. So for the sets of D, the case is totally symmetric. That is, we can view the green passes, the green pass and the pink passes upside down. Then green pass will become from D to D1 to A, and the pink passes will become via some other node D prime and its replication D2 prime and D1 prime. Yeah. So we actually construct the sets of A adding the sets of the internally vertex disjoint paths just inside the sourcing isolating gadgets queue. Therefore, we also add kappa RAD passes from A to D in the rest graph RAD. So this will form a set of internally vertex disjoint passes in the whole graph R cup Q. This is the flow view. And also we can do it in the cut view for another set of the inequality. So we can see this one. For the green one, we cut small a1. Actually, that's because we just cannot cut the source A. We know that. And for the pink passes, we cut everything in A. That is A prime. And yeah, there are sets of A minus 1 of them. Similarly, by symmetry, we can cut the replication D1 in the set big D1. For the sink D, we cannot cut the sink either. And also for the D minus 1 nodes D prime other than D in the sets big D, we can cut everything of them. So if we think about the graph, the residue graph, we will see that there's only one node small a in the set A, and only one node small d in the set D. And also in the set in the sourcing isolating gadgets, the upper bound D1, A, and A2 are disconnected to the lower part A1, D, and D2, just because for every matching edge, we cut one set of it. Therefore, actually the nodes in D1 rest and in A2 rest are only connected to the A, and the nodes in A1 and D2 rest are only connected to the node D. Therefore, also we can safely ignore them when we consider the connectivity between A and D. And so the graph rest is only R with the set A only the source small a, and the sink set D only the sink small d. So if we look at the graph RAD we want, it is totally the graph RAD. So from both flow and cut view, we have proved that this equality is true, and we can really capture the connectivity in RAD, which is the graph we can apply the set intersection filter by the connectivity of the whole graph R cup Q. Okay, so this is the sourcing isolating gadget, which lets me simply cut everything else in A cup D in the final construction. And we will see that for our final reduction from for click to APVC, we're actually constructing a graph H by putting everything together. First, we use a sourcing isolating gadget to ignore everything else in A cup D. And second, we combine two set intersection filters for B cap BD and C cap CD. We can look at the graph on the left, which is an illustration of our final construction H. Therefore, with a sourcing isolating gadget, first, we can ignore everything else in the big set big A and big D. And second, with two set intersection filters, B and B prime on top and C prime on bottom, we can simulate the graph on the right, which remains B cap BD on the top and C cap CD on the bottom. Therefore, if there's an extra flow from A to D, then we can conclude that there's a fork leak. Therefore, we have a dilemma saying that for each edge A and D of G4P, actually we have their connectivity is larger than some threshold, uh, and larger or equal to some threshold, and the inequality is strict if and only if AD is in a for click. We can treat the threshold for adding something adds the connectivity involved by the sourcing isolating gadget and setting intersection filter lemmas. Therefore, if we can compute APVC fastly, we consider all edges A and D, and the threshold for adding NGA cap NG bar D and also NG bar A cap NGD. We compute it with an cube term and consider all edge A and D, and then we can solve the for click problem. There are two corollaries. The first one is for single source vertex connectivity, which asks for the vertex connectivity for all sinks with a given source S. So assuming the Fock-Lee conjecture, it still has an omega n to the 3 minus epsilon lower bound, since all pairs vertex connectivity can be solved by calling it for n times. And also for graphs with general n and m, we can assume the Fock-Lee conjecture and show that the APVC problem has an omega m to the 2 minus epsilon lower bound, and the SSVC problem has an omega 1 to the 1.5 minus epsilon lower bound. This is because we just add some isolating nodes, and n will become larger, but m will not become larger. Therefore, the original complexity n4 and n3 now is still m squared and m to the 1.5. We go on for standard connectivity, and first, the definition of the connectivity is that we compute the minimum vertex connectivity among all pairs of vertex in S, which is the standard set. This theorem says that assuming some new conjecture, which is called the edge universal Fock-Lee conjecture, we have an omega n to the 4 minus epsilon lower bound for standard vertex connectivity for combinatorial algorithms. The construction is from some alternation to the construction of the all pairs vertex connectivity. And below, we will consider the edge universal Fock-Lee problem as an extension of the Fock-Lee conjecture. It is just a graph with a demand edge set E demand, and we ask if every edge or for all edge in E demand, it is contained by any Fock-Lee. The conjecture says that we also have an omega n to the 4 minus epsilon lower bound for combinatorial algorithms for this problem. We note that here we ask every edge instead of there exists an edge. If we ask if there exists an edge in E demand is contained by a Fock-Lee, than is the original for-click instance. Therefore, we actually switch the quantifier into for all in the definition of the problems. We can treat the relationship for click versus the edge universal for click as OV versus something called the hitting set problem, and also sets versus some problem called the quantified sets. They are the same. So remember in our construction for IPv6, we know that any demand edge A and D is in a for click if and only if their connectivity is larger than a threshold. Therefore, we treat the standard connectivity problem as this. All demand edges A and D are in a for click if and only if their minimum connectivity is larger than that threshold. Therefore, we can use standard connectivity to solve the edge universal for click problem. There are two small problems we face when use the IPv6 construction. The first one is the threshold in lemma 3.5 is not unified for all demand pairs A and D. Therefore, we don't know which to compare with the final standard vertex connectivity. The solution is just add two replications to simulate another two sets NGA cap NGD and NG bar A cap NG bar D. Then the threshold will become 5N and unified for all pairs A and D. We can look at this graph and we use J and W to simulate these two sets. So the connectivity will become unified. And also, let A cap D be the standard set. We need to guarantee the minimum vertex connectivity is between some pair A and D, but not A and A prime or D and D prime. The solution is that we add two large clicks to guarantee very large connectivity for A and A prime and D prime, just as shown in A prime and D prime. And they are with very high cardinality. So if we link a bipartite click between A and A prime, then two nodes A and A prime will have really, really large connectivity. Okay, so finally, we introduce the upper bounds. The upper bound results are generally O hat M to the 2.2 for IPv6 and O hat M to the favor 310 for SSVC with high probability. Here we consider the algorithm for IPv6, so we can, and the algorithm for SSVC is really similar. It is by some balancing argument between large connectivities and small connectivities. It is like this. So for pairs U and V with large degrees, that is both larger than K, where K is any threshold, we can see that the nodes with degree larger than K is at most 2m over K. So there are at most m square over K square pairs U and V. Therefore, we compute max flow directly for them. So the time is m square over K square, multiplicating the time of flow, then it is O hat m cube over K square. On the other side, for small degrees, for du less or equal to k or dv less or equal to k, then we know that their connectivity is smaller or equal to k. Here we use a k connectivity oracle, and we extract a lemma that we can compute the k connectivity, which is the minimum connectivity for uv and k, for all vertex pairs U and V in O hat mk cube adding a square term, also with high probability. So at last, we can use balancing to determine the threshold k. For large degree, it is m cube over k square, and for small degree, it is mk cube. Therefore, we let k to be m to the 0.4, and the complexity will be O hat m to the 2.2. So this is the final result for APVC. And also, if the gamma ray Hu tree for element connectivity in Lenatem, actually we can accelerate the small degree computation. That is, we can construct and use the K connectivity oracle in O hat mk square adding a square term. Therefore, for balancing this, we let K to be square root to M. And so finally, the term complexity will be O hat M square. Therefore, we can solve APVC in term theta hat M square, in fact. And also SFCC, similarly, it is in theta hat M to the 1.5. And also standard is in theta hat M square. So these are results in our papers, and thank you for listening.